Today is the 28th. That means we should be finishing up chapter 9, I guess. Does that sound about right? Chapter 10 is obviously in the wrong spot. Needs to be rescheduled here. November. Getting into November soon here. Let's see, we should have another exam coming up here so soon. Let's see what should we do with that? So center of mass, fixed axis rotation is chapter 10, and chapter 11 is angular momentum. I suppose we should have an exam after we do angular momentum. And then we'll do let's see. We're on chapter 9 right now, right? Finishing up chapter 9? Yeah, that's all right. I'm trying to remember which chapters we want to cover because they don't all have actually, I think we might want to be taking a test after chapter 9. We have chapter 10, which could take as much as 2 weeks. And chapter 9 is going to probably take the rest, it might take the rest of this week just with the, I don't know, we'll see. Anyway. But chapter 10 probably take 2 weeks. Angular momentum probably take another 2 weeks. Or another week at the least. So that'll take us to almost to the end of November with Thanksgiving. And then gravitation. Do we have... We'll study gravitation for sure. Yeah, gravitation we'll definitely get into. We'll skip unit... No. In unit 2, we might move into oscillations. We probably won't get as far as waves. We might be able to get it, but not likely. So we might do unit 2, but we will definitely skip fluid mechanics. Chapter 14 we will not mess with. That's a subject for another day. So we're getting close to the end of what we're studying. We might go past chapter 11, but we might not. We might be done after chapter 11. We'll see how that goes. The most likely scenario is that we might cover a little bit of the unit 2 just for fun, but only have a few days to work on it. So anyway, excuse me. So chapter 9 so far has been, let's look at our homework for chapter 9 because I don't think we have anything in there for angular momentum if I remember correctly. We haven't covered that yet, so. I mean not angular momentum. That's not what I meant. I meant, let's see. At the end of chapter 9 we study okay, we do one center of mass problem there. Is that a center of mass problem? Not really. So we don't have any center of mass problems in this chapter yet, which we're going to have to add in. So this chapter is going to have a particularly long homework assignment just because they cover so much, and since we're going to take 2 weeks to do it, that's fine. And this assignment, chapter 9, will actually change. It's scheduled for the 29th and then chapter 10, the 31st. So we're going to change both of those. We're going to change chapter 9 to be the end of this week. Chapter 9 will be the end of this week, which is the 30th.
November 1st.
November 1st, probably, yeah. We'll do that one November 1st. And then chapter 10 will change to,
Is that the 11th day now?
I don't know, I'll check it. Yeah, just say, let's change that to 11.
Is it on the chapter 9?
Yeah, we'll fix it. So October, we want to go into November, probably somewhere along here somewhere, for chapter 10. Chapter 10 is on angular momentum. No, rotational dynamics. I don't know what it is. It's on rotational stuff. And then chapter 11, which is angular momentum, we'll put on. We'll put that one after Thanksgiving, probably, or maybe just before. Or something. Probably after. Because that'll probably be the last one we're saying.
And later you will change chapter 9 to 11 again.
Yeah, I'll do that right now. And then I'll press save. So it actually changes it. Okay. So we have 1, 2, 3, 4, 5. We have about 6 weeks of class left, and we have about 3 chapters and a half left to cover, which is good.
How many tickets I have on their queue last week? 7,000.
Okay, let's see here. Okay. So, chapter 9, we're back in chapter 9, finishing up. We need to do collisions in multiple dimensions. We need to actually talk about this. We didn't really talk about 9.4, so we'll do that really quick. Well, we kind of did. We did that actually. So we're going to do 9.5, 9.6, 9.7 this week. And we'll probably finish these 3 sections probably a little bit early and have a couple of days maybe to work on homework problems. So make sure that you're working on the homework problems, and we'll add some more for particularly center of mass, since we don't have any of those in the homework assignment right now. We'll add some of those and finish up chapter 9 this week. Okay, so collisions in multiple dimensions. We still have all the same rules and laws of physics when we go into 2 dimensions, because our dimensions are 90 degrees from each other once again. But remember that when we have something like your force is equal to your change in momentum in time, your derivative of momentum in time, you can split that into three different dimensions. You can do it in the x, you can do it in the y, and the z, all separately, so that you can break up the force into three force vectors, fy, fz, fx, fy, and fz. And your momentum can therefore be broken into three different vectors. So if your overall momentum is downward to the right, then and that even can be a combination of two changes in momentum or two momentums. You have two different objects with two different momentums. What's the total momentum of the system? Well, it's this one. Well, then you can break down each one of these individual momentums into x's and y's momentums, and then add the x's together, add the y's together, and get an overall picture from the overall components, right? It's no different than adding forces together in their vectors or velocities or anything else. It's all the same. We're just dealing with momentums at this point. So, no different. Here we have the car and the truck that are going to crash. And after they crash, they're going to stick together. The two vehicles are locked together. And then they're going to slide off in some direction. We're going to assume that there's no friction, so that we don't lose any momentum to an external force. In other words, the momentum doesn't get transferred into the earth in this collision. They're just sliding on ice or something. And we have an initial momentum of this car, which is 1,200 kilograms times the 60 kilometers per hour, which you're going to have to convert into meters per second. And then the 3,000 kilogram truck going north at the 40 kilometers per hour, which you'll also have to convert into meters per second to get your proper values for your momentum. And here they show the total momentum as the momentum of the car plus the momentum of the truck in vector form, two-dimensional vector form. They, of course, can pull out, they can actually add the masses together since they are one object. Since they're stuck together afterwards, they can add the masses together for this final total velocity and a final total momentum. And then you have your initial momentum has to equal your final momentum. So this equation looks fairly different on either side, right? But still completely valid. In the x dimension, you have the same equation, except that they pull out the momentum of the truck, because the momentum of the truck, the vector vt, is only in the y dimension. It's only in the y direction. So it has 0x components. So you end up with this equation here for the x direction momentum. For the y direction momentum, you have the truck only and no car, because the car has no y dimensional momentum. When you solve each of these equations individually, you'll get values, you'll get numbers for the x component of the momentum and for the y component of the momentum. And then you can use Pythagorean's theorem to find out the overall momentum's magnitude, which they do here. And you can use those same things to find out the angle using the inverse tangent of the y velocity over x velocity. You only need to put in the velocity because the mass is the same. It's both mass car plus mass truck in this equation, so they only put in the velocity. They don't put in the masses. They cancel out. Now, kind of interesting thing about this is that when you're investigating a car crash, you don't usually do it this way, you do it the other way. Usually you figure out how fast they were going after the collision, after they stuck together. And how do you figure that out? Well, you measure the skid marks, because they're not on ice usually. And those skid marks, the length of the skid marks and the mass of the combined car and truck will tell you how fast they were going after the collision together. And then you plug those into this equation, and you can calculate the speed of the car and the speed of the truck individually. And then you can tell who was speeding. Right? Lazy policemen will not do this, or policemen who are undereducated, who have never taken this class, and they will just assign no blame, or just assign blame by some kind of random thing. If you are ever in a car accident and you were not speeding, you should insist that a accident investigator assign blame. If a policeman shows up and just says, "Oh," just starts asking people questions and assigns blame to somebody, you should insist that they call for an accident investigator if you know you weren't speeding, because they only have a 50% chance of getting it right by guessing, and usually they're just taking people's eyewitness accounts, which are almost always flawed. There's people that lie about it, of course, but nobody ever sees what actually happens in an accident or a crime. Most people don't realize this, but eyewitness accounts are almost never admissible in court as evidence. They're technically admissible in court as evidence, but they're so easily torn apart by somebody else's eyewitness account or by the actual facts of the case, the physical evidence, that they don't mean much in court. The only thing that really means something is something that you can actually measure, something that is actually physical. And you can actually measure the skid marks and calculate the speeds of the cars. So you want to make sure that you don't have a policeman assigning blame and you just accepting that, because that can cost you thousands of dollars or even more. Can even put you in prison. There was a great case by a physicist. A physicist was pulled over for running a stop sign, and the policeman who pulled him over was coming towards the four-way stop in the direction 90 degrees to the physicist. And this is not directly related to this particular thing, but it's related to a different physics concept. And that is that when you're moving relative to somebody else's movement, you cannot tell when they've stopped. It is pretty much impossible. It is absolutely impossible, actually, to tell as a human being, and even a machine has a difficult time doing this, to tell when somebody else has stopped. And so this policeman was driving towards the four-way stop. The other person was driving towards it in a 90-degree angle, and the policeman assumed that he didn't stop because it looked like he just kind of slowed down and then kept going. The physicist took that policeman to court and explained the physics concept to the judge, and said there is no way that this policeman could know whether or not I stopped from just watching me. There is absolutely no way, and even demonstrated it and showed video of different cars that had stopped and different cars that hadn't stopped, and nobody could tell the difference. And he got off without any kind of blame or any kind of ticket or any kind of fine, and the policeman actually had to go to school, which is the right thing. Policemen should be taking classes on understanding these things, because they can actually affect somebody's life really dramatically without understanding this. Another example of this is not related to traffic, but it's very related to law and being being accused of something. It was several years ago in Idaho. A physicist was called on to give testimony to in a murder trial. It was a manslaughter trial. It was a boyfriend of a woman who was babysitting her child, her toddler, and the toddler was found at the bottom of the stairs with a broken skull, dead, and he was asleep on the couch apparently. And his story was that he didn't know anything had happened at all, and that the toddler must have fallen down the stairs and broken their skull. The prosecutor argued that there's no way a child could fall down the steps and break their skull, that there's no way it could happen. There were two huge mistakes made in this trial that were science mistakes. The first one was they had somebody come in and testify that the back of a child's skull is several centimeters thick, when they were supposed to be testifying it was several millimeters thick. And so they got it wrong in testimony, and I don't know if it was deliberate or not, but that made people think that there's no way it could break, just because they said centimeters instead of millimeters. It is several millimeters thick. It's very thin, the back of the child's skull. In the second place, the physicist explained using mathematics that if you drop a ball from 2 meters like that, just drop it straight down, the ball hits with exactly the same speed as it would if you put the ball on a stick and let it fall down. It falls at the exact same speed. How do we know that? We know that from conservation of energy. Potential energy becomes kinetic energy. All of it becomes kinetic energy, right? And we know that that's the case, and if you measure it, it is exactly the case. However, the prosecutor came in and lied to the jury, deliberately lied to the jury by misleading them, and could have been thrown in jail for this. But nobody caught it, because if you're a witness, you can't come in and refute another witness. And the only person who knew that he was lying was the other physicist who'd come in and given testimony about dropping the ball and tipping the ball. So the prosecutor comes in and he takes the ball and he drops it at the same time as he drops a ball on a stick. And of course, the ball that you drop straight down gets there first, and the one that drops on the stick takes longer to get there. And he says, how can they be going the same speed if one of them takes longer? Well, what he was describing is acceleration, not speed. He was saying that the one of them had a constant acceleration, the other one had a non-constant acceleration. And the guy went to prison for 20 years on that testimony with absolutely no other evidence that he'd done anything wrong. Now, it's not whether or not that whether or not he was guilty is not the case. Whether or not that was correct is the case. It's that you must prove beyond the shadow of a doubt that somebody is guilty of a crime for them to be going to prison. This guy was not proven that way. This was completely flawed testimony, flawed science, and it was deliberate. And it happens all the time. Now, I can almost guarantee you that if you go into physics or engineering, you will very likely never, ever, ever be called in for jury duty. Almost never. And I'm 45 years old, which means I have been eligible for jury duty for 27 years. And for many of those years, I lived in big cities where there are a lot of trials all the time. And I have never been called in. Why? Because my name comes up. They look at the people that have come up on their list, and they immediately cross off anybody with a physics degree or a physics background. Anybody. Because they don't want somebody delving into the evidence. Because it makes it difficult to prosecute and it makes it difficult to defend. What's that? Yeah, they want emotional responses and they want people they can manipulate. They want people who are not educated in scientific principles. And particularly in physics principles, because most physical evidence is a physics principle thing. It's easy to mislead anybody with DNA evidence or biological evidence, but there's very little of that ever happens. People think that DNA evidence is a big deal in trials. It's almost never evidence that is, it's either evidence that's inconclusive and inadmissible, or it's evidence that is easily manipulated. So biological and DNA evidence is really bad evidence in cases. Usually leads to nothing. So, but physical evidence, measurements, things like this, things that are things that can be measured using physics and you can draw conclusions from physics. Those things are very common in almost all criminal investigations. If you want to be a CSI, there are places where you can major in CSI. Well, you'll do a lot of chemistry, you'll do a lot of physics, and you'll do a lot of measurement technique kind of things. But that's kind of the background of it. It's very much a physical science kind of degree. Lots and lots of chemistry. Here's an exploding scuba tank, which is kind of like a collision, right? But it's a collision in reverse. You have afterwards, it's all one object, not in this case, not moving, and then it explodes into three pieces, and these three pieces go off in different directions with different momentums. And you can see this one goes this way with this momentum, this one goes this way, and this one goes this way. Three different directions, three different objects, but the total momentum of all three of them combined has to equal 0, because it started with 0 momentum, right? And so that's what they do here. They essentially break it into x dimensions. So this one has an x dimension. It's all in the x dimension, right? This one has an x component and a y component. And this one has an x component and y component. So if you add the x component of this one plus the x component of this one plus the x component of this one, it has to equal 0. And that's what they do here. Then you have to do the y component of this one and the y component of this one, but there is no y component for this one, so it's only 2 for this one. And then once you've set up those equations, then you can plug in the numbers and solve for the final momentums and angles and so on and so forth. What they don't include in here is the actual air moving. They talk about that here. How much of a difference would it make with the air? Well, it depends on how much momentum the air carries, right? The momentum of the air is dependent on its mass and its velocity. And so how much mass is the air compared to the tank? You can, in compressed air tanks, you can definitely feel the mass of the air. You can definitely tell when they're full or they're empty. It's definitely there. Most of the mass is still in the tank. So it's probably, I would say, less than 5% or 10% of the tank's mass is air. Depends on how much pressure there is, I guess. Okay, so now this is the biggie, center of mass. We'll start this off today, and then we'll take some more time tomorrow and maybe Wednesday as well to work on it. If you have an object, a system with different masses in it and different momentums in it and so on and so forth, you can actually calculate where the center of the mass of the system would be, which means if the mass was distributed throughout the system, where would the center of that system be, right? If it was distributed equally throughout the system, there would be a center to that system. Where would that center be? Another way to think about it is an object that has a strange shape, it will follow the path of a point particle about its center of mass, as if all of the mass was at its center of mass. So here's a great example of the cat, right? You have a cat here, and they're throwing the cat, or dropping the cat. They're moving along here in a train maybe, and they drop the cat, and as the cat drops, it follows this parabolic path, you could think of it as. But you can see that the cat twists and turns and rotates and everything as it does this. And so if you measured where the foot was, or the tail, you can see the tail's here, and the tail actually moves up, and then it moves down suddenly because the cat twists, and then it's way down, and then the tail moves back up again. So the tail is up and down and up and down, so you can't follow the tail. Similarly, you can't follow the feet or the head or anything else. But the center of mass, which is somewhere near the belly of the cat, will follow this nice parabolic trajectory just like any falling object would. It's the same with the tank. If we go back to the previous example with the air tank, compressed air tank, the center of mass of the tank is at the center of the tank somewhere here before it explodes. And after it explodes, if it started here, if the center of mass started at the origin, the center of mass will actually remain at the origin because it was at the origin before and it wasn't moving. So the center of mass will remain where it is as long as there's no external force being added to the system, as long as some wind doesn't come by and blow something in some direction or something. The center of mass will remain where it was if it started off not moving. Or if you have the center of mass, for example, of a rocket. So we've done the rocket problem in the homework. Don't remember which one it is, the last one in chapter 9. So the last problem in chapter 9 has this rocket, which would be going, which after the rocket motor shuts off, it would go in this parabolic path above the Earth as long as it was falling back to Earth. If it was out in space, it would keep going in a straight line. But no matter what direction the center of mass would be going, after the cone breaks off, the center of mass will still follow that same path. Except that one of them will go off in this direction, one will go in this direction. The overall center of mass of the system combining these two pieces will still follow that same path. And it may seem like it doesn't, but it does, as long as there's no external forces involved. If there are external forces involved, or if you're creating an external force with like fuel or something, then you do have to consider, you have to take into account all the fuel, where the fuel is going, where the exhaust is going, and it will still follow the rules. And it can get very complicated. But this idea of a center of mass is still very, very valid. Objects tend to follow physics, they tend to obey the laws of physics as long as we consider the center of mass as the point of the object's movement. If we don't, then it starts to get really complex. Still follows physics, but to show that it follows physics becomes a very difficult task. So what we do is we consider any mass that we have as a collection of many, many tiny little point masses, right? So if you have a mass like this ball is the big mass here, then it's made up of a bunch of tiny little point masses that are shaped into the shape of this ball. And each one of those masses may actually have the same shape and same size, whatever, but they don't have to necessarily. And they don't have to be uniformly distributed in any way either. They can be all over the place. They can make the shape of a cat or make the shape of a house or whatever, whatever the object is. They don't have to be distributed in a nice ball shape or anything like this. In fact, you don't even have to think about their shape if you don't want to. But the idea is if we add up all those masses, then we're going to get the total mass. And if we start thinking of the force acting on this object, this ball or the house or whatever it is we're exerting a force on, as a bunch of little forces acting on the little pieces of that mass, then we can start to think of the momentum as a whole bunch of little momentums, a whole bunch of little particles, each with their own momentum. And then if we can add them together, of course, we can build up the total momentum. And of course, this leads to calculus. Calculus is this idea of breaking something into smaller pieces so that we make it simpler, and then adding all those simple things together to make the whole, which is actually quite complex. So, in the middle of this here, they actually talk about two different types of forces. They talk about external forces and internal forces, because you can have internal forces. But remember, whenever you have internal forces, there's always an equal opposite pair when it comes to internal forces. For example, if you explode your rocket apart, and that explosion is the internal force, it's going to shoot one of the rocket particles one way, one of the rocket pieces one way, and the other rocket piece will be shoved the other way. And those forces will be equal and opposite, as will the momentums. So those internal forces can be included. But in the end, what you get is the net force is equal to the sum of your internal forces plus your external forces. And the internal forces, of course, cancel each other out with their momentums cancel each other out. So when you actually take the derivative of the momentums in time, you actually get the net force is equal to the sum of all these derivatives of each of these pieces of the momentums in time. The internal forces, of course, end up being zero because of those canceling pairs, those equal and opposite pairs. The external forces do not cancel, so they're the ones that contribute to the momentum. So the overall momentum of the system is only due to external forces, and it's the change in momentum of each piece of the whole in time. Add them up. The same is true for the center of mass. The center of mass has a momentum, where if you add up all the momentums of the object, you will get the momentum of the center of mass. So the force is simply written as the derivative, the time derivative of the center of mass momentum. So how are we going to use this? Well, if force equals mass times acceleration, and force also equals derivative of the center of mass momentum in time, then mass times acceleration equals derivative of the momentum of the center of mass in time. So then you get this, you get it down, broken down into this equation here. Well, this is interesting because if you take the time derivative, out of this summation, which you can do that. That is allowed. Then you have a momentum alone inside of this summation. The momentum alone inside the summation is the mass times the derivative of the displacement, or the velocity, in other words. So then the masses, of course, are all constants. They can come, well, they don't come through the sum because each one of them can be different, even though they're constant. But anyway, they're constant. We take the second time derivative through, though, because the time derivative can come through. That means you have two time derivatives, so d squared d squared dt squared on the outside, right? Where in the inside you just have the sums of the masses and the displacements, or the masses and their positions is actually a better way to say it, is equal to the force, the mass times acceleration, right? So your second derivative of your position now, this was displacement, this is position. But anyway, the second derivative in time of your position now on the right hand side times mass is equal to your acceleration. Right? Then we can divide both sides by the mass and calculate the acceleration of the object. This gives us a formula for the acceleration of an object. The second derivative in time of 1 over the total mass of the object times the sum of all the little masses that make up the object times the position of all those masses. And that begs the question of what is this thing here? What is this sum of all the masses and their positions of the mass? Right? Why does it beg that question? Because we've divided by the total mass on the outside, but we care. This suggests that we care where these masses are located, because it's each little piece times where it's located. So this suggests that we really care where the mass is located when we're talking about masses. This is what we call, this is kind of our justification for caring about the center of mass, where it is, why it matters. And so we can actually solve for it. We can actually pull that out and say this does tell us where the position of the center of mass is. Because the masses divide out. If you add up all the masses inside this sum, you get the total m. So these masses actually will cancel out. The only thing that doesn't cancel out is where the masses are. So this calculation actually tells you where the mass is, or where the center of mass is. 1 over the total mass times the sum of all the masses times their positions. Now for simple systems, this is a very easy calculation to make. Here's a very simple system. 3 distinct point masses, mass 1, mass 2, mass 3, at 3 distinct locations, R1, R2, and R3. We can easily add these positions and these masses together because there's only 3 of them. No big deal. So what does it look like? It looks like mass 1 times R1 plus mass 2 times R2 plus mass 3 times R3 all over the sum of the masses. That's the big M. The big M is M1 plus M2, M plus M3, and this is the summation of M1, R1, M2, so on and so forth. The top part is this thing. The bottom part is this thing, 1 over M, right? So there we've done it. And this will make a vector. We know how to add vectors together. We can break these vectors into their individual components. If the component of if R1 has components 5i hat plus 6j hat or something like that, then we can just put that in here, and then we add, each one of them will have something like that. We add all the I hats together, add all the j hats together, we're going to get a vector divided by a scalar, and we're going to get an overall vector here for our center of mass position. And we'll do that for each individual dimension. We'll have an x component one, a y component one, a z component one, and when we add them together, we'll get an overall vector which will tell us where the center of mass is. And you can actually calculate the velocity of the center of mass by taking the derivative of that, the time derivative. And you can get the velocity of the center of mass. You can get the acceleration of the center of mass, which we already calculated earlier. So let's do something with this that is more realistic. Let's talk about the moon and the earth. What time is it? we've got time to do this one. So here we have, we're going to determine how far the center of mass of the Earth-Moon system is from the center of the Earth. So compare this distance to the radius of the Earth. We got two masses. We have the radius r, which is going to be so the center of the Earth is going to be the center of our coordinate system. That's going to be our origin, right? So for the mass for the Earth, we're going to have the mass of the Earth times the radius of the Earth. So the edge of the Earth is, let's see. So actually, we're not going to use the edge of the Earth. We're using the center of the Earth because we want the center of where it is. So the mass of the Earth times the radius to the Earth center from its own center is 0. This one ends up being 0. And then the mass of the Moon times the radius of the Moon from the center of the Earth. So you got to measure the distance from the center of the Earth all the way out to the Moon and put that in there, and they put in those numbers. So the radius that we're going to end up with is going to be 4.64 times 10 to the 6 meters, which is going to be essentially the center of mass of the Earth-Moon system. So the radius of the Earth is actually 6.37 times 10 to the 6. This is 4.64 times 10 to the 6. So the center of mass of the Earth-Moon system is actually inside the Earth, but it's not at the center of the Earth. It's about 2/3 away from the center of the Earth towards the crust of the Earth. So as you watch the Earth go around the sun, this is what it looks like. If you look at it very closely, let's see if we can find a good picture of it. They're not showing a very good picture of it here. Earth. Here you see some of the effects of it. You have this precession, but the Earth, here it is right here. The Earth actually goes around the sun with this kind of weird. Oh, here's a better one. This kind of weird movement, right? The Earth doesn't go straight around the sun. It actually wobbles a little bit back and forth. And that wobble is because that's where the sun, or that's where the Moon pulls it out of its orbital path. In other words, this orbit here would be more like the center of the center of mass of the Earth-Moon system. Kind of wobbles back and forth. Well, makes the Earth wobble back and forth. This one here would be the center of mass of the system. This one would actually be the Earth, and it's not as drastic as that. You can't actually see it because it's so small. You couldn't actually measure with your eyes. You've got to have a better version of this. Yeah. Anyway, here's actually what happens. This is the path of the Earth's center is the green one. This is the one we want. So that's the center of the Earth. It actually wobbles back and forth. The path of the Moon's center is this weird, funky thing. Boink, 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 boink. But the path of the center of gravity of the Earth and the Moon goes around in this nice, clean orange orbit. So that's the one. I'll copy that image and put it in the book. So, anyway, good fun. We'll talk more about center of mass and we'll calculate some center of masses tomorrow.